project to finish. There is PowerPoint. Okay, so we'll start on the advanced diploma. And as you know, there are 3 subjects. Right? We start with the advanced radio, and then up to June we continue there. In parallel, you can start project at any time. Project is, I will introduce project next time because there are some more to come. Being the provided today, they are unable to come. So I postpone the introduction up to next week. Right? There are certain criteria to meet. Some of you might already know that from last year. I will introduce how the project should go. And the starting time is your decision. You can start project at any time. Theory we will cover in 2 steps. From January to end of May we will do advanced radio, and then June you can take that subject, and then from July to November we will do advanced telecom systems, and December you can take that subject. So those are the only 2 theoretical subjects you have to finish. In between, at any time, you can finish your project. Project is kind of, there are only 1 or 2 lectures to introduce and get an idea about the expectations of City and Guild, what to deliver. But we have to individually show 160 hours of work on the project. So we have to keep the proof. I will introduce you all that procedure next time. Okay. Those who did the diploma, I heard that there was one question which was little tough. Router programming, maybe easy for you. There was a router programming problem, I think, which all students said it is tough, but other than that it is okay. Right? Then in the radio, advanced radio, which we are starting now, it's highly linked with the radio diploma. Some of you may not have done radio. Some of you directly joined to the advanced diploma, therefore I will revise that area also. Not spending a lot of time, but I will spend a bit of a time until we equalize ourselves. Right? Otherwise it's difficult to catch up. Right? If I introduce the main area, we start with propagation area, radio propagation, and then from there we move on to microwave link, and from there we move on to satellite communication. Again, you may remember, those who did the diploma, SATCOM was partly done there. And the last area, which is the biggest area, is the cellular communication, where we study mainly 3G, 3rd generation cellular. And those who did the diploma, 2nd generation cellular was covered in the diploma. So it's again linked, and about 2 or 3 questions of the paper will be mainly on that area. It's the biggest area. Okay, so that's the main outline of our syllabus. And when we do 3rd generation, we will be discussing technologies like CDMA, wideband CDMA, which is called WCDMA, and network planning, different stages of CDMA 3G network. Likewise, it's very interesting, cutting edge technology. So that part will be definitely very useful for your career. But there is a little amount of work you have to do self if you have not done the 2nd generation one, 2nd generation cellular in the diploma. Right? I will highlight those as we go along. So you can write the main heading today. Main heading, antennas and propagation. Antennas and propagation. In fact, these are two theories, but since our courses are targeted for the job, we will do the combination of the 2 theories in such a way that how it is used in practice. So our focus is mainly to get an idea about the think of these 2 theories for practical purpose. But from the diploma, we have knowledge on each area, I'm sure. Antennas was one topic we did. Propagation was another topic we did. So in the advanced diploma, we combine the two topics and see how we can put them into practical use. But let me revise a little bit of the diploma so that we'll lay the platform to go ahead. First of all, a little bit on the antenna. What are the different types of antennas we already know? Just to revise. Dipole, monopole, what else? You can name few. There are large amount of antennas, so you can find one or two names. Loop antenna we did in this diploma, loop antenna. Marconi antenna we did. Rhombic antenna we did. What else? Just came in from there. You look up on top of that ADJ building, there is a tower. And already there are about 10 different types of antennas. So if you did not notice while coming, maybe while going out you can notice. There are microwave dishes, and there are planar arrays used for the cellular, all on that tower, on top of that building. And there are just single wire antennas. Sometimes when we don't have signal in our radio, we might just put up a wire, isn't it? And that is also an antenna called single wire antenna. So likewise, the antenna theory is a big one, very large one, and you people study antennas even up to postgraduate level. And the area we will cover are mainly the microwave antennas in this advanced diploma area, which is UHF and microwave antennas. So we are not covering very low frequency antennas or low frequency antennas or HF. Those bands we don't cover, and it's mainly UHF and microwave region that we are supposed to cover in this syllabus. So let us be very clear about our scope, because this is a very large area, so we have to limit it for the study purpose. Okay? So advanced diploma syllabus is limited to UHF and microwave antenna. In the antenna theory, you may remember very basic theoretical antenna we studied. What was the name? Theoretical one, it's not practical. We call it isotopic, isn't it? We call it isotopic theory. So we will start with that. Just to revise. Okay? We can write updating isotopic theory. This is diploma stuff, so we are going through it again. But just as a summary. Okay, what are the main properties in the isotopic? First we said it is a theoretical or hypothetical antenna that we imagine. It is not actually there in practice. It's the imagination. Second is, it is omnidirectional radiation. It radiates omnidirectionally in all directions. Third is, it was a reference antenna. It was a reference antenna used to measure the gains of other antennas. Remember we discussed when we want to measure the length of this disc, we need a unit length, isn't it? Without 1 meter or 1 foot defined, we can't measure the length. So you need a unit length. Same way, when you want to measure how good an antenna radiates or receives, to measure that you need a unit. Isotopic radiator is a unit. With respect to that, we measure the gain. So it was the unit. It was having unit gain, omnidirectional radiation pattern, used as a reference antenna to define the gains of other antennas, but it is fully theoretical. So those were the key points we studied. Shall we just summarize them in point form one at a time, rather than writing a note again? And the next first thing you can see is the hypothetical antenna. Hypothetical antenna. Second point, it has unity gain. Unity gain. Within brackets you can mention capital G equals 1. Gain is 1. Third one, radiate omnidirectionally. Radiate omnidirectionally. Omnidirectionally. Within brackets, equal in all directions. Equally in all directions. Fourth point, radiation pattern is a sphere. Radiation pattern is a sphere. Sphere of radius 1. Radius 1. 1 means unity again. You draw that. Draw a sphere of radius 1. Isotropic candela at the center. This is the symbol of isotropic. We put a star at the center, that is the symbol of the isotropic radiation. G equals 1. Therefore, it's a sphere of radius 1. Although we draw a circle, it is in 3 dimensions. It's a sphere. This diagram is to indicate that it radiates equally in all directions. That's why used as the reference antenna. Used as a reference antenna. To measure the gain of other antenna. Used as a reference antenna to measure the gain of other antenna. So that's all about the isotropic radiation. Then first of all, to make things simple, we will assume all the radiations we discussed are in phase space. Not on ground. So we are not talking about a tower like what you see on top of ADJ, because it's close to the ground, close enough so that it will have special effects due to the ground. But let us first simplify the thing, assuming that free space propagation is there. That means we are talking about a place where there is nothing other than this antenna, which is difficult to imagine, because I think you have never been there. You have always been to places where some other things are around. So free space is quite different, something you have to imagine and understand. This is how it happens. Right? But mathematically it is the most simple. So let us start with that. You can try submitting free space wave propagation. Free space wave propagation. Free space wave propagation. Since we are combining antennas with propagation, I am doing little part of antenna, little part of propagation also. Right? So this one is propagation on free space. And that you can write. Let us assume a free space situation. Let us assume a free space situation in which following assumptions are valid. following assumptions are valid. We'll write down. Number 1. There are no objects. There are no objects around to cause any reflection scattering or diffraction, scattering or diffraction, I will explain this word later, of the radio wave, Reflections, I think you understand. What is meant by scattering? Scattering means reflecting to all directions. Something like, suppose even if you take a tree, when a radio wave hits that, most of the energy might go, but some energy gets scattered a little bit and lost. But you can't calculate from which direction it comes. Even a raindrop can come. When you have a raindrop, most of the energy will go, but some energy will still scatter. So scattering means reflections without any pattern. It happens in all directions. Scattering. Then diffraction means bending of the wave fronts around an object. If you have a mountain or something, when you send a wave like this, it slowly bends it. So that the path is little bent. It's called diffraction. So all these things happen because of the object. If I assume free space, these things will not happen. That is our assumption. At the same time, we will assume in the free space there is no matter, like air, so that there are no molecules to absorb our energy. So zero absorption. Since there is no matter, next sentence, since there is no matter, energy absorption is also absent. There is no matter, no matter, energy absorption is also absent. So in summary, we are talking about a place where there are no absorptions, reflections, diffractions, refractions, and energy scattering. So none of those are available. So if you can imagine a place like that, that is a free space. So maybe you can summarize in points. No reflection, no absorption. Likewise, all these words you can just mention, they are not there. So just to summarize the set of words we encounter in propagation. Some of these words, if you did not do the diploma, it may not be clear immediately. I will slowly explain them, right, as we go along. How many things are there in the list? There must be 5 already. First one is reflection, refraction, diffraction, absorption, scattering. Reflection, refraction, diffraction, absorption and scattering. Those are the effects. We have in normal troposphere we live. But each one is a very complicated one. Therefore, we have to analyze them thoroughly. we try to get meddle with everything, we can't analyze the performance. In fact, there is no theory so far in the world to understand propagation fully. Nobody understands how the signal is coming from the tower into your cellular. So, to predict the signal strength of at the cellular phone, we use statistical models. There is a model called HATA model, and all these planning tools that cellular operators use are statistical. Why statistical? Because we don't know the reason. When we don't know the reason, we use statistics. Statistics deals with the cause. This deals with the result, not with the cause. Isn't it? Suppose, for example, statistician might analyze the variation of marks of city angle this paper worldwide, and they will put it into a graph, find out what is the distribution. But they will not know why did that happen. Cause is unknown. When you are not looking at the cause, but you are looking at the effect, you use statistics. When you look at the cause, why did that happen? Then it is more analysis, deeper analysis of reasoning. Right? So understand it like that. Right? Cause and effect. Right? There is a cause that you see, which is coming which is causing an effect. It is causing an effect. And when you analyze the variation of the effect, you call it statistics. When you look for the causes and try to control the causes to control the effect, that is science. We try to explain it. How did that happen? Right? Scientific reasoning we call it. So these are general ways for you to think. Because there is statistics in your syllabus also. In the diploma you did some amount. Even if you didn't do so far, you will have to do someday. Because you can't escape from statistics in your life, in your career. Right. Simple reason. There are many effects in the world for which causes are not known. Therefore, you have to do the statistics someday or the other. Because you have to deal with the effect in your job. So don't try to avoid. Statistics is initially a bit difficult, but once you get into terms with that, it becomes easier, and you can get a lot of meaning out of it. Why I said that is because when you study cellular, you will find that the behavior of the received signal at this location when I take a call is statistical. Causes are yet to be analyzed. We can't write an equation directly. So variations we analyze statistically. We may be able to derive what is the average power in this place. We can calculate. But the power right now is not the average power. It will vary. And the variation is very difficult to analyze. Nobody knows. Later on you will learn there are distributions like Gaussian distribution and Rayleigh distribution in order to find out the signal strength in a particular place. Okay? So therefore the things are very complicated when these 5 things we wrote are there. When they are not there, it becomes so simple. So that's why we are trying to say they assume a case where none of them exist. Okay? Then we will take an isotropic radiator and feed some amount of power like PT into that, and then consider the power at a distance and find out how much is there. Okay? You can write something power density. You can write consider an isotropic radiator. Consider an isotropic radiator, fed with the power of PT1, power of T for transmitting. Consider all the points at a distance of distance of capital R, at a distance of capital R from the antenna. This point form a spherical surface. Spherical. Spherical surface. What do you mean by that? If you take a isotropic radiator, we are feeding a power of PT watts into that. PT watts. Then we want to find out what is happening at a distance of R, at a point like this. But it is not only at that point which is remaining at the distance of R, is it? Because it's a sphere like this. Complete sphere with a radius R. All the points on this sphere are at the same distance from the antenna. Take a ball, and all points on the surface of the ball are at the same distance from the antenna. So can we do that? Radius should be R. And assume that this is the point I am interested. So you may call this point A, this point B, and it is also at a distance of R. What I am interested in finding is the power density at this location on this surface. What is the power density? We normally call it stress. Write it as power density. I am sure electrical power you already know, V squared over R, I squared R, that kind of thing. But there is no such thing called power in the space. Power is there in a resistor or a circuit. When you talk about power in space, we always talk about power density. How much of power per unit cross-sectional area? Power density means power going through a unit cross-sectional area. Power going through a unit cross-sectional area at this point. Power going through a unit cross-sectional area at this point. That is what we call power density. So what will be the unit? Measurement unit? Watts per meter square, isn't it? Because area is meter square. So unit is watts per meter square. These are not theoretical, because right now there is a power density even inside your body because of the radiation from everywhere. So we are not talking about very theoretical things. You are right now feeling it. Of course you are not feeling it, but it is there. It is there. So we all are exposed to the certain amount of power density from every antenna. Every antenna we are exposed to. Right? How do we calculate this power density? How do we calculate power density at this point? If we know that there is a power of PT that I am feeding into this. How do we find? Simple idea. What we do is, we know that this is radiating equally in all directions. So there is no particular direction in higher in strength than the other. Equally in all directions. And all that power PT should be penetrating through this surface, isn't it? All that power PT should be going through that surface. And what is the surface area? Surface area of a sphere? 4 pi r square. 4 pi r square. This definition here, surface area equals 4 pi into r square meter square. To take a sphere in geometry, this is the surface area. Remember, this is not circle, although we draw it, this is spherical surface, right? It's the surface of a ball, right? Imagine a tennis ball and the surface area of that is 4 pi times radius square, right? And our argument is that this power PT must be going through this surface area uniformly. Therefore, if I divide PT by this area, I get power per unit cross-sectional area. Simple way of calculating. Simple, right? Since the power PT penetrates, power PT penetrates, penetrates, this surface uniformly in all directions. Uniformly the power density at any point on the surface, density at any point on the surface is given by this one can explain it. Power you have with this PT, you divide that by the surface area of that ball, which is 4 pi r square. Answer will be in watts per meter square. So this is the equation for power density at a distance of r from an antenna in free space, from isotropic antenna in free space. If you take the 10 log of this, you can get it into dB watts per meter square. From this, if you take 10 log it, then answer is 10 log of this answer, then it is in dB watts per meter square. Log of power density having unit dB watts per meter square. Later when we do satellite communication, microwave links, we will use that unit dB watts per meter square. I'm just introducing basic, which we will be using in numerous other places. So if you miss a basic, you miss many things. You miss many things later. So the basic should be very strong in our mind. Okay. Next basic we will discuss. Now little bit of propagation we did now. Now we switch back to little bit of antenna second. Okay. So next one, gain of an antenna. Next subheading, gain of an antenna. Again antenna. How do you define gain? Suppose the examiner, now that you have gone through the diploma, if the examiner asks you now, define the gain in one sentence. If the basics are clear, you can. Otherwise, you will go for the theories you can. Suddenly found that certain parts are forgotten, and you will be putting unnecessary pressure on yourself, especially in the exam time. Pressure builds up, when you don't remember what you crammed. So therefore, solution is simple, not to cram. Solution is not to cram. And there may be few things to cram, but identify them very clearly, because every cramming you do is putting unnecessary pressure on your resources, on yourself. Maybe I have said this earlier, right? You make your life a bit miserable by doing so. And why should we, isn't it? Why should we? We should study, I think I mentioned, we should study smart, not study hard. People who study hard get tired. It is like running a marathon with high speed, 100 meter speed. And you know that you are not going to go far. But if you study smart, correct speed, good technique, you can run very long, lifelong. You can become a lifelong learner, and you can enjoy it all. So think about these things. The idea is to understand something rather than cram it. Once you understand, you can twist it in any using words and put it in answer script later. But without full understanding, if you try to cram and go to the exam, maybe advanced diploma is not possible, or maybe CEM is not possible there. There is a limit coming. And it depends, depending on the person, but there is a limit. So we don't set our limits high. This is what I mean. And this is the most difficult subject in the City and Guild syllabus we have started. This is why I am saying it. The pass rates are very low world over. One of the most difficult subjects, because everybody tries to cram it. Everybody tries to cram. That's why they make their life miserable and make it difficult for themselves. So don't cram. Don't cram. Try to understand the actual happenings by visualizing it, rather than trying to cram words. Because words can't really explain what is happening. More and more words you cram, you are putting a lot of unnecessary pressure into yourself. Coming back to this, here now we are trying to combine two theories, I say. Little bit of antenna theory and little bit of propagation theory. We did little bit of propagation yesterday. We are coming back to that. But before that, we try to define another part of antenna, which is the gain. So how would you define the gain now without cramming it? What do you feel about the gain? If you have no feeling about it, maybe you have just tried to cram. Maybe you are not yet ready for the advanced. I am just asking, putting a little challenge to you, right? So take it in that sense. Okay. How do you define? My question remains. How to define gain of an antenna? What is the feeling? We already know the unity. Unity gain we already know. So if you want to measure the length of this table, how do you measure? You take 1 meter rule. You know how they measure the cloth, isn't it? They measure the 1 meter rule and keep repeating it. Same here. If you want to measure the gain of an antenna, you measure the gain. You take the reference, which is the isotropic radius, and find out how many times better is this antenna compared to the isotropic. That is called the gain. It is called the gain. So the gain means how many times better the practical antenna is radiating with respect to the isotropic radius. That is called gain. You can write. Gain of an antenna is of an antenna is an indication of you put a inverted comma, okay. Put a inverted comma, say how many times better, indication of how many times better the given antenna, how many times better the given antenna radiates with respect to the isotropic antenna or isotropic radiator. With respect to the isotropic radiator. With respect to the isotropic radiator. Example, the dipole has the maximum gain of 1.64, maximum power gain of 1.64, along its axis. Remember that figure, 1.64 along the axis. What does that mean? Along the axis, its radiation is 1.64 times better than isotropic radiation. Right? Okay, this means it is radiating 1.64 times better. It is radiating 1.64 times better along its axis compared to and you can complete it as compared to okay, so if you have to read that sentence to complete it, you know the message. That means you have not been reading while you are writing. Some of you had to go back and read it again to complete it. If you are one of them, maybe you should change. Maybe you are not reading while you write. It's a bad practice. And then, please read. So what is the answer? Compared to isotropic radiation. Isotropic radiation. Okay, so we'll draw that situation. So if I replace this antenna now by the isotropic radiation, by the dipole, and this is the dipole axis, what would have been the power density? Earlier power density was Pt divided by 4 pi r square. Now new value. New value is 1.64 times better. So just multiply this by 1.6. So write that. You can do it like this. Just consider the axis. You don't need to draw this ball now, because it's not radiating equally in all directions. So we consider only the axis, but it's a point which is on that surface of radius r. Earlier it was Pt over 4 pi r square. Now it is 1.64 times better there. I just multiply by 1. So similarly, if there is any other antenna here, it will be that gain multiplied by PTO of pi r square, isn't it? So you can write similarly, an antenna having a gain capital G. Similarly, an antenna having a gain capital G would produce a power density of G times Pt over 4 pi r square watt per meter square. And you must remember that gain is a function of the direction. So you have to find out the correct gain in that direction before you apply this. Because gain is not same for a practical antenna in all directions. Therefore, it's a function of the direction. You can say since gain depends on the direction. We consider we should substitute the gain in the correct direction to this equation. Okay, so now we know if there is a practical antenna of gain capital G, what would have happened to the power density at distance r? In fact, the earlier power density will be multiplied by G, that's all. Right? Because it is G times better now. Right? G times better. Okay, that's power density with a practical antenna. Okay. Next, sometimes we may be required to calculate not power density, but how much is the electric field strength at this point, or how much is the magnetic field strength, because we know it's an electromagnetic wave going. At a distance r, there is some electric field strength, there is a magnetic field strength. So they might want us to calculate that instead of the power. But we just calculate this power per unit area. But electric and magnetic fields are also important. By the way, what is the unit you use to measure electric field? Right now we have electric field here, and if you use a field strength meter here, you get a reading. What is the unit on that reading meter? We did in the difference. Electric field size. We said there are positive charges, negative charges, and I gave 5 rules of the flux. Unit is think about it. I am sure you know, right? Not sure. Even if it is not sure, you can say, right? Because this is not the exam. Tesla was actually magnetic. Gauss. Gauss is field. It is not the field strength, but it is the charge. Not Gauss, it's Coulomb. Coulomb is the charge. Weber is also magnetic. That means you remember, because Weber was also there, right? So it's coming close. Right? Now it is like exam, isn't it? We are trying to remember something we crammed, but it is not coming. This is the example I made. You have made your life miserable. Volts are there, but volts, actually it's volts per meter. Yeah, you are correct. Volt meter is slightly different. Volt per meter. Correct. Volt per meter. But why do we try to remember it like that? Let me show you a simple method. Because I think you have missed that simplicity, that's why you are complicating it. Now, if you take 1 meter, say, just take 2 points 1 meter away from each other in the sky, just take point A and point B 1 meter away, will there be a voltage between these? Right now, say my finger is pointing to two places. Will there be a voltage between these? Tricky question. There will be. Because there are lots of radiation in this place. All radio channels you can hear if you put a radio. You can watch TV. You can take calls. All these signals. Therefore, there must be potential difference. Electric field is being radiated there and it is right there. So, what you have to remember is that it is a voltage across 1 meter length. That is electric field strength. If you fail to remember that basic, you never remember the units. Units are very easy because it's a voltage across 1 meter length. So once you remember that it's a voltage between 2 points 1 meter away, then it's very easy to find the unit. So very easy to understand. Right? Remember that. Right? Volts per meter. Magnetic. I gave you a comparison in the diploma. If electric is volts per meter, magnetic is amperes per meter. Simple like that. Amperes per meter. Or ampere turns per meter. Right? Suppose I multiply the two. What do you do? I multiply the two, I get volts multiplied by amperes divided by meter square. Volt into amperes is what?
What?
What? It's what? Watts per meter square, which is the unit you have just derived. Watts per meter square. Power density was watts per meter square. That means power density is actually electric field strength multiplied by magnetic field strength at that point in the sky. Okay? Very easy to remember. Voltage multiplied by current is power. Voltage per meter multiplied by current per meter is power density. Simple way. Simple way to remember. Okay? You can write something. Field strength or field intensity at distance r. Field intensities at distance r. Field intensities at distance r. Maybe I will give you a shortcut. Try to remember it this way rather than trying to cram complex things. Right? In a circuit, you know you have used the voltmeter, I am sure. Right? You know there is a voltage between points. Between any 2 points, you will have a voltage, potential difference. But in the space, you can't have a voltage in one place. You can have potential difference between 2 places. So it's volts per meter. Volts per meter, which is field, electric field strength. Instead of voltage in the space, you talk about field strength. If you are talking about a circuit, you can talk about a voltage. But in the sky, we talk about field strength. In the circuit, you mean current. In the space, you find current per meter, which is magnetic field strength. Electric field strength is E, magnetic field strength is H. In the circuit, you talk about the power, and we talk about power density, watts per meter. Watts per meter square. Power is what? Here it's amperes per meter square. Next line you may say, I will write it here, power equals VI. in normal circuit or resistor. In the space power, so watts per meter squared is equal to volts per meter multiplied by amperes per meter, which is giving us a rule that power is electric field multiplied by magnetic field. So this means power density S has a unit of electric field intensity, it is this, multiplied by magnetic field intensity, E into H. So power density will be E into H. So these are shortcuts which bypass a lot of theories. Similarly, you may have equation power equals V squared over R. How do you convert it to space? Instead of power, what do you have? Power density. Instead of voltage, you have electric field strength, E. So power density is E squared over. Instead of R, we use Z naught, impedance of placement. Can you see how to convert? If you remember one equation, the other is nothing. You don't need to plan. Power is replaced by power density, voltage is replaced by volts per meter, resistance is impedance of phase. Similarly, you may have heard power is I squared into R in a circuit, but in space power density is I, instead of current you have magnetic field. So magnetic field squared divided by effective, because into effective. Look at units. This is volts per meter squared divided by R. Volt squared over ohm is what? Volts per meter squared becomes meter squared. Therefore, answer is watts per meter squared, which is power density. So why should we complicate this simple thing? I'm sure you have studied electric fields in the school, magnetic fields in the school. But it may be that this integrated thinking that is lacking, so please develop it. Because in the school we discuss these at different topics. Now is the time to link them and absorb them fully. And try to use them, make devices like antennas or transmitters. Okay, so these simple rules we can apply to calculate electric field intensity at a distance d. Remember, we are discussing about free space at the moment. So let us take this. E squared over Z is equal to S. If I want electric field intensity, I will just multiply S and by Z naught, just cross multiply and take the square. Volts per meter. So take the power density multiplied by impedance of free space, take the square. That will give us electric field intensity at a distance d, at a distance r. You already know this value. What is the impedance in free space? In the diploma we noted free space is not fully free, isn't it? It has impedance. It has opposition to the wave energy going through it. How much? That is something we have known. 377 exactly. 377 now, which is equal to 125. 125 ohm. So remember that. If you didn't remember that, 125, which is also equal to 377, is the impedance of free space. That is the opposition to the flow of energy in free space. So unfortunately, even the free space is opposing propagation. There is opposite. Maybe propagation of electromagnetic waves is the only thing free space is opposite. But it is there. So if you design a link which is to communicate with a distant star or something, you have to consider all that loss. So there is a 125 ohm impedance is coming from electromagnetic. So we are not going to prove it. Remember, right? Good that some of you have remembered already. Power density you already calculated. So can you substitute your earlier answer to this place and simplify and find out the equation? Power density you already have in the last equation. It was G times Pt over 4 pi r square. So it's your turn now to put them together. Certain things to simplify, you can simplify to the minimum. Gt divided by 4 pi r square multiplied by 125. That is 5 you can see. Square root and then 20 over it is 30, right? Square root 30 G Pt divided by R. 30 Gpt divided by volts per minute. So if you know the antenna gain and the power and the distance, you can find what is the phase at that distance. Okay. So little exercise to you now. We started saying our subheading field strength, isn't it? There are two field strengths. I started with this equation, but can you start with the magnetic field equation and come into H? We want H here instead of field. H is the magnetic field intensity. So these are the areas difficult for the people who missed the diploma. So those who missed it, maybe you have to refer a little bit on the diploma. No. But if you are already familiar with the fields, it is okay. You can continue. What is the other equation I gave? H squared into Z0 equals F. I squared R is equal to power. I squared R is equal to power. Therefore, H squared into Z0 should be equal to power density. Easy way to remember. From the earlier table you can get it. I want you to find H. So if you don't like it, you can use E into H is power. V into I is P. Just convert it to E into H is power density. So if I want H, it is H divided by E. I have already found E, so just substitute. Another way to find. is GPT over 4 pi r square divided by this. Also become 4 pi. Something like this. You can get into a single square. Then divided by this. One of the r's will cancel. GPT square root will cancel with GPT and leaving one square root of GPT. So try to get it into single square. In any case, you might not need to use this formula because we first find E, and since to find E we already calculate S, we can directly use this formula to find the answer because we will know S and E, it can be found directly. So this final formula need not be remembered at all. It is just to practice. Okay, so it is 1 over 4 pi r times square root GPT over 30. Is that correct? 1 over 4 pi r times square root GPT over 30. So anyway, don't try to remember the equation. Right? These equations are just to practice. Okay. We'll do a little exercise now. We know few equations of two-phase propagation. Assume that I take a dipole, put it in free space, then this is a lambda by 2 dipole in free space. Lambda by 2 dipole in free space. And we will assume a distance of something like 100 meters from there. It is not very far. From here you can imagine 100 meters. Right? 100 meters, and I want to find out what is the signal strength in this case, power density in this case. I take a point like P. I want to know what is the power density and what is the electric field strength, what is the magnetic field. And I am feeding, I will take something like 50 watts. We'll make it 100 watts to make it easy. I am feeding 100 watts into that. But so far we are considering free space. But this is very useful calculation. At a distance like 100 meter, what is the power density? For operation like another receiver, we need to know this. Even if you don't do any radio, you might still want to know this. In fact, last week, 2 weeks ago, I got a call to the department. I got a call from a lady from Ratmaland. She was a lawyer, and she was asking me, now there is a tower being constructed close to our home. What is my exposure? What will be the electric field in my house? That kind of question. So then I said, if you are in free space, this is the amount. Since you are in the earth, this is the amount. Like that. But of course, it is not a technical discussion. But she was worried. She was worried. What is the field strength level? That will that be damaging to the health and all? So people who are not interested in making radios are also now interested in these calculators. So there is a practical value in that. In fact, every week if you read the newspaper, there is an article going about the hazardous fields being created by telecom operators. Every week. Some paper is published. And in fact it is this. What is the field strength? What is the power density? Did you think about these things earlier? Now it is time that somebody will ask you. If you say I am doing advanced diploma in telecom, you are sure to get this question from someone. What will be, is it risky to be 100 meters away from the antenna? Some kind of, are you ready to ask it? So let us do it now and get familiar with it. Again, I already gave you it. Gain in the along the axis, the gain is 1.64. It is 1.64 times better than the isotopic radius. Already I gave. Fortunately or unfortunately, City News will not ask you to do this calculation. They are very kind. They don't want you to do calculation. They will give the answer sometimes. Say, what do you think about this? Some question like that will come. Right? So you may be required to interpret that. Whether it's good or bad. But to be considered for ourselves, we need to do this calculation and make us consider about it. So if you take 1 meter squared in this area, 1 meter by 1 meter, there will be power going to that. So how many watts will go? Or how many microwatts actually? I don't know, maybe milliwatts. Milliwatts. 1.3 milliwatts. Did you all get 1.6? Stethoscope. I think you remember my last example, right? An engineer without a calculator is equal to a doctor without a stethoscope. Nobody respects. Still some people don't remember. If there are doctors to be without stethoscope. So please bring them. Have them in your pocket. At least left pocket, if the right pocket has the cellular. There is another pocket, so carry your calculator. Okay, 100 meter away from the dipole, it is radiating 100 watts. Some say it is 1.3 milliwatt per meter square. Others agree? Do you agree? Okay. So many have got that same answer. 1.3 milliwatts will be going to a cross-sectional area of 1 meter square. Even if you take this area of a board, it will be very close to that, like say, slightly higher than 1 meter square. And about 1.3 milliwatts are coming through that. That is the idea we should get. 100 meters away. Right? So compare this with practical imagination. Right? Okay. Then can you find out the electric field strength? How many volts per meter? If you take 1 meter length, what kind of voltage difference or potential difference will it create? That is square root 30 PTG over R. 30 PTG into R. So use the second formula and get practice to use that. This is a practice exercise. So you will be very confident about what you learn. Is it millivolt? How many millivolts? 0.7 volts per meter. Is it correct? 0.7 volts per meter. So if you take 2.1 meter away, there will be a potential difference of 0.7. You do that 10 times. Okay, now find H. Easy way is E into H. Oh, not 0.7. H1. It is 1.86 milli. Easy way is now you know E into H is S. So H will be S divided by E. You have both these answers. This answer is the first part, this answer is the second part. Just divide the two answers, you get it. So that big formula you derived, you don't need to use. This is easier. In fact, what happens is here there will be electric flux, like electric inlet, there will be electric flux vertical, magnetic flux horizontal. Right. So it is creating a flux pattern. So what you calculated are those field strength, electric field strength, magnetic field strength, and the power density. Why do we need to know this? As radio engineers, we need to know that because we need to know whether our receiving antenna there is getting enough signal strength to operate. Because at the moment we are not putting any receiving antenna, later on we will do. And knowing the signal strength is important so that we can adjust it to a level where receiver is working okay. That is the idea. That will come later. Okay, so this summarizes all our calculations we did. Power density at a distance of d, field strength at a distance of d, electric, field strength, magnetic at a distance of d. Right. Okay. Then there is a little term called EIRP, we will use that also, subbearing effective isotropically radiated power. In bracket EIRP, effective isotropically radiated power. You can do the same figure example. Your earlier calculation you can draw again. You took a dipole, fed 100 watts, 100 meter distance away from that you found out phase strength and the power density. So just draw it as a summary again. So let me ask a little question from this example now. If I want to get same power density, same field strength, same magnetic field strength, in fact these two are automatically coming when power density is there, so even if this is there, it is enough. Instead of using a dipole, if I use the isotropic radiator here, should I increase this power to get that same answer, or should I decrease?
You have to increase that power.
You have to increase. Why? Because earlier it was 1.64 times better. Right? So therefore, in order to get that amount, what should I give here? Increase by how much? How many times should I increase? 1.64 times. So if I feed 164 watts, that answer will remain same, isn't it? So you can say this is equivalent to that. Because earlier it was, that antenna was 1.64 times better, so it created that field. This one is not. So I have to increase the power with that proportion to get that same field. So this is the effect of using a bad antenna. If your antenna has less gain, you have to use more power. What is the difference? Antenna is something you buy once and install. Power is something you spend continuously. So you have to pay your electricity bill every month. It's a recurrent cost. Antenna is a fixed cost. So therefore, when you design, be careful. Use the best antenna. That will save power. For several reasons. One is your recurrent cost will increase. Second is that you will be radiating too much of power to the space. That's also bad. So various factors come in. You are polluting the environment unnecessarily. All those things come. So we must use the best antenna. Right. So equivalent to this, and same answer will come. Same answer. So what is this equal to? This is equal to, in theory this is, earlier this is 1.64 times 100. That's how it happens. 1.64 is G, 100 is earlier PT. So if I multiply G into PT, it is called effective isotopically radiated EIR. That's equal. Which means if I take isotopic radiator and feed EIRP into that, I will be getting the same power density as the actual antenna in the place I am considering. To get the same power density there, how much power should I feed to isotopic radiator? That is called EIR. Right? So you can write therefore EIRP is the power to be fed to an isotopic radiator. Place PLACED place at the same point as the practical antenna. In order to produce the same power density at the given receiving point. So that's how EIRP is defined. So in mathematics, it's a simple relationship. EIRP is G into P, which is simply saying that increase your power by an amount equal to G in order to make it equivalent. Increase your power by an amount G. So that's the term we sometimes use, EIR, effective isotopically radiation. Okay. We'll have a short break there. We did the theory of power density, field strength, electric and magnetic at a given distance from an antenna which is fed with a certain power. We did the example also, and also we introduced this term EIR. With that we'll have a short break. We will start in about 15 minutes.